All right, so this is the notes for the class that we're going to be missing due to commencement that I have to attend on Thursday, May 1st. So I just wanted to go through and kind of let you know kind of how this is going to work. We did do some of this at the beginning of class on Tuesday. So I'm not going to cover all of this again, but you can read through it. We're going to be finishing up the 7A1 to 7A4 and then the 7B1, 7B2. Now, as we're going through this, I will be skipping some problems that I've highlighted. Those are just like what we would have had in class. They're the Kahoot questions. So feel free to work those as you go through the video, but then remember there's a QR code or link, whichever way you want to join, to a individualized Kahoot. It'll just be you by yourself in there that you're going to complete after you've watched the video. So any of these highlighted questions, expect to see those in the Kahoot. So just to give you a heads up on that. Okay, so just to remind you, we were talking about in class how essentially these contingency tables can be used to help us look at um, medical testing. And we said that, the body state, which on this side, they have that as rows, either a person has a disease or they do not. That is, your body can't be in both states at the same time. And you might get medical testing done to see if you have it or not. And so the test may come back positive, which indicates the test believes that you have it, like a blood test or a nose swab, whatever they're looking for. Or a test comes back negative, which means they do not think that you have what they were testing for. And so then we talked about in class how you could have true positives, which means you are sick and the test correctly identified that. Or you could have a false negative, which says the test tells you that you're fine because the test is saying you're not sick, but you actually are sick. Your body is sick. You could have a false positive, which is when you test positively, which means that the test thinks that you're sick, but your body does not have that state of illness. And you can have a true negative, which means the test says you're not sick and your body is not sick. So those are also, again, in agreement with each other. So if you're looking for a false positive or false negatives, those are actually conditional probabilities. The false positive is the number of false positive results. That means the number of times that out of the positive test, people were incorrectly told you have disease, but they do not. Okay. And that goes over all positive results because again, you're hyper focusing on just people who have a positive test result. And then we have the false negatives, which are the number of false negative results, which remember means people who got told you're fine, but they're actually sick, over all people who got negative results. Okay. So we're going to look at this first one right here. It says an oncologist wants to determine if a brand new test is effective in detecting whether or not a patient has cancer. So again, we have some stuff to fill in on this contingency table. We need to fill in these missing pieces. So remember, this has to sum to 50, so that would have to be 3. And this has to sum to 50 again, so that would have to be 43 because that's a 7. Notice that adds to 46, so that makes sense. And then these two both total to the same number, which is 100. Okay, so they tested 100 people. Find the probability of patient testing positive, but they do not have the disease. Remember, that's called you tested positive falsely. So that's a false positive because you're actually not sick. And the way you find that probability of a false positive, I'm just going to abbreviate, is you take all positive tests, which would be hyper focusing on this top row. There'd be 54 people who tested positively on the medical test. And we're looking for the ones that were incorrectly getting a positive result. In other words, they got told you are sick, but they're not. So that's these 7 people. Okay, so we're going to leave that in its fraction form. Find the probability that a patient tests negative, but they have the disease. So that's that false negative. So you received a negative result, but you're actually sick. So again, only focusing on negative tests this time. And so there's 46 of those in total. And a false negative means you were told you don't have disease. So you're told you're fine. That's what negative testing means, but you're actually sick. So there are 3 people who are in that overlap. They were told they're fine by the test, but their body actually has disease. So there's 3 out of 46 for that. Okay, now this next thing, and example number 2, this is just a different frame. It's not a false positive or false negative. This is how accurate the test is. So this means if you tested negative, we want to know how many people got a true negative. So it's the opposite of the false negative. It's actually a true negative. So the negative predictive value means getting a true negative. And so this is for West Nile virus. So we do still have to fill in some missing pieces. A lot of these have that on these tables. And this time we're going to, I don't know why my P is missing, but that's supposed to be positive test results and negative. I think my chart got squished. But we're going to round our final answer to 4 decimal places on these. I don't think it said that on the last one. No, it didn't. So that's why I left them as fractions. So we need to figure out positive test or negative test. This is for West Nile virus. So subject either has the virus or they don't. This has to add to 19, so that's going to have to be 17. 17 plus 6 is easy to do. That would be 23. And then we need to figure out these missing 3 spots right here. So we have 677 minus 23 will give me that number right here. There's 654. Subtract 2 from that, and that'll tell us how many people had a negative test result and they were not sick with West Nile virus. And then we also need to add these to get this total. And then I'm going to double check that 19 plus 658 is the 677 as well. Okay, so 677 people were tested total, but we're talking about a true negative, the negative predictive value, which means the accuracy that the test tells someone they are free from this virus, and they truly are, is the true negative or negative predictive value. So probability of the negative predictive value, again, I'm just abbreviating. We still only focus on just negative results. So there's 658 of those. And we're focusing on the people who got the right result. So they were told, you are not sick. That's what a negative test result is. And they actually don't have West Nile virus. Those are in agreement with each other. So these are people who were told the true status of their body matched with the test that they took. So 652 divided by 658, we want to get that to 4 decimal places. So this is going to be 0.9909 if we round. So almost 99%, essentially 99% accuracy if we were talking about it as a percentage. But they just wanted it in decimal form. Okay. So I'm skipping over this next one. You will be trying this one on your Kahoot when you're finished watching the video. So let's look at number 4. So an oncologist wants to determine if a brand new test is effective for detecting whether or not a patient has cancer. Use the table result to determine the probability that the test gives a false positive or a false negative. Okay. This is combining what we learned in 6B with what we're learning about false positives and false negatives. So we need to find the probability of a false positive or a false negative. Okay. Now, good thing about this is these two cannot be the same. You cannot have a positive test result and a negative test result on a like a swab or a blood test at the same time. If they're testing for calcium or whatever they're testing for, you can only get one result for each item that they test. So we know there's not going to be any overlap that we have to subtract out. So this will be very simply just get the both of the probabilities and add them together. So we have to remember how to get both of these. So for the false positive, I might use some highlighting for these. Let's see. For the false positive, you have to focus on just positive test results. I'm going to highlight that. And so look, that would be out of 135 people tested positive altogether, but we're wanting to know which ones of those were incorrectly identified as a positive. Remember, positive means you are sick. So 22 people had their test results say you're sick, but their body is not sick. Okay, so we've got that group. And then, excuse me, let's highlight in a different color, yellow. So the false negatives, we're focusing on the negative group. That's the negative test. So that's this row. And there's 105 of those. And remember, a false negative means you were told you are fine, there's no disease, but your body actually is sick. So that's those 7 people. Now, unfortunately for us, this is one where they wanted the final answer as a simplified fraction. And we would need to either use our calculator, which I expect you guys to do because you have the scientific calculators. But if you don't know how to do this, I can always show you too real quick on the video. If you need to find a common denominator, you can always list multiples of the numbers until you find a match. So, so like we would do, those are supposed to be colons. Why it's connecting them. But essentially 135 times 1 is 135. 135 times 2. We're just going to make a list. That would be 270. 135 times 3. And again, this is the old school way of finding the common denominator. You just start making a list of each multiple. 135 times 4. I usually go to 5, and then I'll jump over and try the other number for a little bit. But like I said, I expect y'all to use your calculators because that's why you have them. So that's going to be 675. Okay, so we're going to make a list on this group and see if we find a match. So 105 times 1 is, of course, itself. 105 times 2 is 210. Again, not matching any of the ones up above yet. 105 times 3 is 315. 105 times 4 is 420. Not found a match yet. 105 times 5 is 525. I go a little further because I haven't reached high enough to pass this number yet from the other line. 105 times 6 is 630. And then we have 105 times 7, 735. And I'm writing these down so I'll be able to know what number gave me what. 105 times 8, we'll go to 9. Then we'll go back up to the other number and see if we can find a match. So this is kind of the old school way we used to find least common denominators before calculators could be programmed to do that. And times 9 is 945. So let's go back up here. So this we stopped at. This was times 1, times 2, times 3, times 4, times 5. So let's do 135 times 6, which is 810. And 135 times 7, which is 945. So we finally found it, okay? So again, you could just multiply these two bases together to get a common denominator, but you're going to make it really big. So if I multiply them by the least common denominator values, that'll help us keep this a little bit smaller. But again, I do expect you to use your calculator. So this was 1, 2, 3, 4, 5, 6, 7. So we need to times this fraction on top and bottom by 7. So I did that piece so you can see it. This one we had to go 1, 2, 3, 4, 5, 6, 7, 8, 9 times top and bottom by 9. Our common denominator is that 945. On top, we've got to do 22 times 7, which is 154, plus 7 times 9, which is 63. And then we add those together. And that's 217 over 945. And I believe that's in its smallest terms. You'll have to double check that on your calculator. But we use the least common denominator to hopefully avoid having to reduce stuff down further. Okay. So again, use your calculator to get that. It'd be a lot quicker. So let's talk about the next part. I'm going to highlight that too so it matches. All right, so let's keep going. So now we're in 7A2. These are shapes of distribution. So a lot of this section of homework is going to be telling the right shape versus the word that they use to describe that shape. So if your data is essentially a big mound in the middle or just anything where you can fold the piece, it's like, imagine folding a piece of paper here, like right down the middle. If you fold those over, the two sides kind of match. That's symmetric, that's balanced. Usually that's what we're looking for, especially if we're going to do statistics later on. Skewed right and skewed left means you have more data pulling your average higher than your median, than your middle. So notice if you're skewed right, you've got a tail pulling much further to the right than you do to the left. So you see that our middle, our median, somewhere still near the I guess you call it the mound or the hump of the distribution, but the average is going to be pulled up. It's like, imagine if you had people taking a test and a bunch of people made like 100. A bunch of people make 100, they're going to pull the average up, but that may not be where the middle score is. Okay. And if you're skewed left, it's like if you had a bunch of people just not show up to take the test, and so they all got zeros. So they're going to bring your average down. So notice our tail is pulled much further. There's a lot more data pulling to the left than there is to the right. Okay. In this scenario, your median is still here in the middle, the mound part or the hump, but the average is being pulled down. So it's going to be further down. So then they summarize this for us right here. They say the mean is significantly smaller than the median, you're going to be skewed left. Okay. Now, when we say significantly, we mean not like 0.5 away from each other. If you've got like 33.5 for your mean and 34 for your median, that's not significantly smaller. That's 0.5 difference. I would say, if we're more than 5 away, or even maybe more than 4 away, that like 4 points, that means we're significantly smaller. Okay. Now, if your mean and median are approximately the same or very, very close, you're going to have balanced tails. So you're going to be symmetric. Okay. So if your mean is smaller than the median significantly, your tail is going to be pulling to the left, you're skewed left. If your mean and median are approximately the same, your tails are balanced on each side of the hill, and you're going to be symmetric. If the mean is significantly, again, we're talking about more than just a couple, like decimal points away, significantly greater than the median, we're going to have a tail to the right, which means we'll be skewed right. Okay. So we're going to try this one. It says the following data set represents salaries at a company. Now, these are in thousands of dollars. They just didn't write out all the thousands. So that first one is actually 38,000. They just left off the 3 zeros since they told us it represents thousands of dollars. So determine if the following data sets represent a distribution which is skewed left, skewed right, or symmetric. So we should find the mean and median and compare them to determine the data distribution. Now, I'm already guessing we're going to be skewed right just because I'm looking at these low salaries down here and then these major jumps on the right side, which is the bigger numbers on a number line. Those scream somebody's making a lot more money than the average, than the median kind of salary. So let's actually prove that though. So the mean, remember, if you're finding the mean, you're adding up all the items and dividing by how many you have. So we have this many salaries. We have 38, 39, 41, 45, 46, 57, 98, and 121. And that's a total of 1, 2, 3, 4, 5, 6, 7, 8 salaries. So we're going to be dividing by 8 because we're just doing a regular average. So 38 plus 39 plus 41 plus 45 plus 46 plus 57 plus 98 plus 121. That's 485 on top. Divided by 8. And I'm not going to round this or anything. They didn't tell us to. So I'm just going to write it out that it is 60.625. Okay. So that's our mean. Now your median, remember, is based off of the middle. Luckily, these are already in order from least to greatest. I just double checked that. So we don't have to do anything special there. We just have to know how many numbers we had. We had 8. So when you have 8, remember the median is somewhere in the middle between the two middle numbers because we have an even set of data. So we take those two middle numbers, we add them together, and we cut it in half. Now that's going to end up being 45.5. You can check that on your calculator. So notice the mean is significantly greater. So the mean is greater than the median. And remember we said if it's a significant amount of difference, which I would agree, this is way more than like a few points difference, then we're going to be skewed in the direction that those that we had those outlier kind of values, those the things that pulled our average up since it's being pulled way, way up. So that's going to be skewed right. Our tail is going to be more stretched to the right. Okay. All right, this one's going to be on your Kahoot. Again, you can look at kind of the shaping. Notice there's the whiskers. This is a box and whisker plot. You can think of whiskers kind of like tails on each side. So you can see this tail is pulling way further this direction than it is on that side. So that should help you when you go to answer these. These will be separated out as 3 separate questions on the Kahoot. Okay, now this one. When I did this, there were only a couple of these in the homework. And they're kind of a weird one because you don't technically have the graph in front of you. You don't have the shape in front of you. They're giving it to you as a frequency table. So I want to show you, and I'm going to do D just because I have more room down here. I'm actually going to graph this one as a histogram, which is part of the next section, actually. So we're kind of getting a little preview of that. And I'm going to show you how I can look at that graph and I could have actually told the answer, how I could have figured the answer out without graphing it. So sometimes seeing the visual helps you see how we could have done that. So we need to make sure each of these values, if we were making this a histogram, even 0, they need to have their own mark at the bottom. So these are our values. So 0, 1, 2, 3, 4, 5, 6, and 7. So these are our values. in a frequency distribution or histogram, a graph, we put the frequency on the y-axis. And you can't really put all these numbers because they're not evenly spaced. So we need to get up to about 30 because that's highest value I see is 3. The number 3 occurred 28 times in their list of data. Remember, if you actually listed these out, there'd be 4 zeros. You made a data set list. There'd be 12 ones. Like it would take you forever. Okay. So we don't want to do that. We want to use the frequencies. So I think I'm going to count by 5s just because I need to get up to 30. So 5, 10. We need to count by something equally spaced. 20, 25, and 30. Okay. So 0, the value 0 occurred a little less than 5 times. It occurred 4 times. And usually when we make these little histograms, when you go to do these in the next section, you don't create them yourself. You're just dragging, there's like a little applet kind of thing. It's a Desmos graph. You just have a little button on the top of each bar and you can drag it to the height that you need to. So that's all we're expecting you to do with those. But that's a height of 4. 1, it needs to be about 12. So a little less than halfway between 10 and 15. Okay. 2 needs to go all the way up to 23. So that's a little more than halfway between 20 and 25. 3 needs to go to 28. So that's a little over half between 25 and 30. And then 4 needs to go to 17. About right here. And 5 needs to go to 7. So I'm just rough estimating the height of each of these bars. 6 needs to go to 6. So that's just a little bit above 5. And 7 needs to go to about 3. Okay. Now, when I look at this, I kind of see that this to me looks like we might be skewed to the right a little bit. Now, let me show you how I could figure that out from this just data, just from the items, the values, and their frequencies. So what you're going to do when you're trying to determine this is you're going to look for the highest frequency, which is this 28, and then you're going to look at the 2 numbers on each side of it. If they're almost identical to each other, you will include both of them in what I call the top of our histogram, kind of like that hilltop, okay? If they're very different, only use the one that is closest to your original highest value. So since 23 and 17 are pretty different from each other, this is going to be my hilltop, okay? Then what you're going to do is you're going to add up the values that we would have in our list to the left of our hilltop and to the right of our hilltop. So this is 16 values. So there's 16 values to the left, because left, remember, think about numbers from least to greatest. These are the smaller values. So they're going to be to the left of the hilltop. Okay. There's 16 values to the left. If I add this up, that's going to be, let's see, 24, 30, that's 33 values. We have way more values to the right side of that hilltop. Okay. So that makes this skewed. And they didn't ask us to do skewed right or skewed left on this. They just said, oops. They just said you needed to tell me if it's skewed or not. So this is skewed. Yes, skewed. Okay. All right. So notice that I put a note here. Newton says that B and D are skewed and A and C are not. So let's talk about why the A and C are not, but the B and D are. Okay. So look at this one. I'm not going to graph these. So the highest frequency here is 24. And if you look on each side of it, 18 and 19 are both pretty close to each other. So I'm going to include that whole group of 3. It's either going to be a group of 2 or a group of 3 for your center. And that just depends on if these 2 points on either, or the 9 and 11, if they have similar frequencies to each other. Okay. The highest frequency is always the top of the hill. Then we're going to add these together. So this is, let's see, 7 plus 9. That's going to be 16 plus that's 31 values. Now, as long as this, and usually they say within 4 to 5 value points, as long as it's within that of 31, it's going to be symmetric, mostly symmetric, okay? So if we add up how many items we have to the right of our thing, remember this is going from least to greatest, these are the actual values. So remember, they stand for these little numbers at the bottom. The number of items we have tells us how tall our bar is. So that's the frequencies. So this is 29 values. So because these are very close to being balanced, this is not skewed. This one would be symmetric. Okay. Let's look at C. 24 is the highest frequency. That goes with the value of 9. So 9 is the bar that's going to be the tallest. Okay. 20 and 20 are about the same, so I'm going to include all three in my hilltop. So this is 10, 11 values to the left. This is 13, 14, 15, 16. Now, like I said, this one would be one that sometimes people might want to argue on and be like, no, I think it's skewed right because there's more values there. Newton's general rule is if it's within 5. So if they're within 5 values of matching, so 16 minus 11 is 5, then we would say not skewed. Okay. All right, let's look at B though. Notice B, the highest value is 26, but you can't use both 17 and 19 because their frequencies are very, very different. So we're just going to use the one that's closest to 26. That's our hilltop. This has 17 values to the right of it. And this one has, let's see, that'd be 27, 28, 29, 34 values. So that's way, way skewed different. Okay, it's almost double the amount of values on that side. So this one is, yes, it is skewed. If you needed to know, it would be skewed left because the lower level values on the left side of the mound or the hilltop, those are the ones that happen more frequently. So your tail would be dragging out more to that side. Okay. All right, so this one's kind of a weird one. We don't usually put this on the test, but I just wanted you to realize you can tell this without graphing, but if you really wanted to, you could graph them to verify the shapes. Okay. All right, so that takes us to 7A3. We're creating or interpreting histograms, which we kind of just practiced doing that ahead of schedule. We're going to talk about this, supposed to say frequency tables, not tabs, and then relative frequency. So a histogram essentially is just a way for someone to visualize a frequency table, a count. So here's an example. Let's say I had all these test scores in a class, and Miss Nerd's class decided, now this is called a class interval. They ranked the grades based on like an interval, and then they counted how many they had in each interval. So for like 50 to 58, the only number in that interval is the 53. So that's why this tally is 1. They just did like a tally chart, and then they said, okay, that's one item. Whereas 59 to 67, I'll do that one too. 59 to 67, there are none, okay? So I won't do that one. Let's do 68 to 76. So 68 to 76, 68 to 76, 68 to 76. So there are 3. So 1, 2, 3, and that's how they got this as well. So notice that's how you'd start. You just take your data, you count out, and again, they may not give you intervals. They may just have, especially if it's a lot of repeating numbers, sometimes it would just be one number per line, like we saw earlier in the previous section. But if it's not like, if you don't have a ton of like repetition, sometimes they do these little groups like this, okay? So notice the groupings or scores are my labels. Those are my values. The number of them is the height of each bar. And notice the green bar is here. It's just at 0. Okay, so that's not an empty space. It's just the green bar is on the x-axis. And then notice these heights match with these frequencies. Okay, so in Newton, you'll have, like I said, a few questions where they'll already have this table for you. And you will just be pulling, you'll have a little circle on the graph it's actually movable. You'll click on it with your mouse and lift it up or down to match the correct frequency height. Okay. Now, here's some problems we might encounter where we just have to look at the actual given histogram, and we have to be able to tell someone, you know, how many people fall in a specific interval. So our values down here, 4.5 to 5.5, 5.5 to 6.5. So these are miles that were ran, I believe. Yeah. So selected runners from a marathon were asked how many miles they could run before they started to feel tired. So that's these results. Okay. So how many of those runners could run more than 7.5? And less than 8.5. So we're in the 7.5 to 8.5 grouping. So that's from here to here. And notice that's just one bar. So we just need to find the height of that bar, which is right here at 5. That represents how many of the runners said that they fall in this range. Okay. I feel tired between 7.5 to 8.5 miles. We look at the next one. Says how many of these runners could run less than 6.5 miles before they, so anything less than 6.5. So here's this, we would be doing any bar to the left of that. So that's both of these bars. So there's 5 people in this first group from 4.5 to 5.5. There are 4 people in that second group. So this would be 5 people plus 4 people, or 9 of the runners. Okay, so we just read that. And again, the 5 would be runners too. But remember, Newton doesn't always have you write the units. Okay. All right. So then now let's look at a frequency table and see if we can figure out how to attach this to probability. Because probability is something we just learned about in the last chapters, in chapter 6 stuff. So we got all these quiz points. So we have a teacher who gave 30 students a quiz. It was an 8-point quiz, and then these are the scores. I've already taken the time to put the scores from 0 to 8 down here, and I went through and tallied those for you and made a frequency chart. Now, if you didn't have this here, you would put your 0, 1, 2, 3, 4, 5, 6, 7, 8, and then you would go through and you'd count. Okay, I have 2 zeros. So then I'd put a 2 there. So you could create that yourself if you needed to, but to save time, I did it. Okay. All right, and then it says, let's use this to answer some questions. So how many times does the data value 7 show up? So 7 is a singular value, but there were 4 students who scored a 7. So that was 1, 2, 3, 4, if you look up there. So 4 times, okay? Of the 30 students, how many scored greater than a 4? So that's not a 4, that's greater, just greater. So that would be students who scored a 5, 6, 7, or 8. Now, those are the scores. We want to know how many students did that. So we have to add together 3 plus 2 plus 4 plus 16. And that looks like that's going to be 25 students, okay? What percent of students scored better than a 4? So that's the greater than a 4 again. So percent is like probability. So probability that someone scored greater than a 4, that'll give us either a fraction or a decimal, but we can turn that into the percentage. So there were 25 students out of a total of, remember they told us this was 30 students, but you could add all these up to see how many students are there. And then we're going to take that and turn it into a decimal first and then into a percentage. So I'm going to write that to maybe 4 decimal places, dot, dot, dot. And they didn't say, so let's round to the nearest 1/10 of a percent. So that would be about 83.3% roughly. Okay. So you can take these values, you can add up the number of students in each category or each score. We can divide it by the total number of students that were involved in the test, and that will give us the probability, or you can turn that into a percentage, okay? Because we can get fraction form, decimal form, or percent form from the probability. Now, the next thing is, and I'm not going to read each of these lines to you because we're just going to do it. What we just practiced, you can do for each individual frequency. You can turn each frequency into the probability as a decimal for that specific thing. That is called the relative frequency for that. So if you sum all your frequencies together, so notice this was the number of goals Real Madrid scored in each of their soccer games from April to May of 2016. Given the frequency table below, what is the corresponding relative frequency table? So we're finding the relative frequency for each one. So what I did first was I added up how many games they actually played, because these are scores. This is how many goals they made in a game, but this is how many games they played where that was the total score they got. So they had 2 games where they made only no points. They had no score on the board. There were 4 games where they only scored 1 goal, okay? And so we're going to take these and turn them into probability by dividing them by the total number of games, which I said if you sum that, that is 18. So we'll need to do 4 divided by 18 for this one, 6 divided by 18 for this one, another 4 divided by 18, and 2 divided by 8. Now we already have that one. That one's up there at the top. I already did it. That's 0.111. But let's check the other one. So we're turning these into decimals because that's easier to connect them kind of to percentages. So this one would be, if I round it to the same decimal places they did before, I'd be 0.222, which means this one's also that since it's the same fraction. And then 6 divided by 18, 0.333. Now, I want you to note something. If you were to add all of these up, it should equal 1 or very, very close because we did round these. We could be at 0.999 or we could be at 1.001. It's possible to be a little under or a little over when you're doing these rounding steps. So if I have 0.111 plus 0.222 plus 0.333 plus 0.222 plus 0.111, notice I'm almost 1. And the reason I'm not exactly 1 is because these were repeating decimals and I rounded off every single one of them, okay? So that's why I'm just a little shy. but that's essentially 100% of the data they collected, okay? Now you see this column right here is blacked out because we're going to do this next. This is called the relative frequency. Cumulative relative frequency means as we go down each row, we are adding the previous row to the new data, okay? So here's what I mean by that. For this first row, we've only accumulated 2 out of 18 of the gains, right? So it's still at 0.111. But once we get to row 2 here, we've now got a total of 6 gains, which is this first probability plus this one. So that's 0.333. It's accumulating. Notice you just take this sum, because that's the biggest one we've got so far, bring it down, add the new number of gains to it, which is 6 out of 18. And now we're at 0.666. And now we're going to add 4 more gains to our list, which is this value we got here. So we have this sum from the previous row plus that. Notice we're at point, that's supposed to just be 1 point right there, 0.888. And then the last one, we're adding the final 2 gains. So notice we get 0.999, which rounds to 1. So this probability adds up to 18 over 18 in its fraction form, okay? So essentially a cumulative relative frequency just means you're adding total number of frequencies and you're just going to be accumulating all the way up to 1, okay? We don't ask you to do much with this one, like on an exam or anything, but this is something you would see definitely if you go on to stats, okay? You definitely should be able to take and find the relative frequency of each of these. All right, this one is going to be one that is on the Kahoot, so I'm going to skip over that. Okay, so that gets us into 7A4, the normal distribution. This is something that most people have heard of, even if they didn't call it the normal distribution. If you've ever been in a class and had somebody ask the question, oh, does our teacher grade on the curve, or are you going to scale the grades? A lot of times what they're talking about is this nice, smooth bell curve. So essentially what they're saying is you've got these histograms that look symmetric, but we're going to actually approximate things using a nice smooth curve, the normal curve. And it only works when our data is symmetric. So some things to note about the normal distribution that are important. The middle right here, that highest peak, if you go down and find that value on the x-axis, that value will be your mean, your median, and your mode. They are all exactly the same if your data is symmetric. Okay, they're the same value. You'll have some symmetry about the center. So there'll be 50% of your data will be to the left of your center line, 50% will be to the right, and that's this part 3. So that's, again, that symmetry. You actually never touch the x-axis. Not that I'm going to test you on this, but this actually floats just right above the x-axis forever. But the area under the whole curve, if you add, and this would take calculus to prove this, from the left all the way to the right adds up to probability, which is 100% or a 1. So the total area under the curve is 1. Okay, now we'll use that to our advantage when we do some simple tables. We're going to learn how to do some stuff with this where we learn how to read a table. Okay, and that's going to be in the part 2, the 7B1. So standard deviation, not something we're going to test you on how to find. We're not going to make you find it in this class, but just realize it tells us how spread out our curve is. So the smaller your standard deviation, the more narrow and tall your curve will be. The wider or bigger your standard deviation, that makes a much wider bell curve. It's still got the nice symmetry, it's just wide, okay? And then if you really did want to calculate the standard deviation, there's a formula for it. You do not have to know how to do that for this class. We will provide you with the mean and the standard deviation. We also told you the Excel way to find it if you're really curious. You'd have to enter in all your data into Excel first, like in a column, and then say equal standard deviation from A1 to A12 or whatever your data is. But you do not need to know how to do that part, okay? So we're going to learn a couple different things. The first thing we're going to learn is how to rough estimate certain percentages on a bell curve. These are specifically related to being at the mean and taking 1 to 2 to 3 standard deviations to the right of your mean or to the left of your mean. And what we mean by that is, say my mean is 20 and my standard deviation is 5, okay? If my mean is 20, so let's say that that was given to us. I'm just giving us a rough example here, so this will make sense. And our standard deviation, which we usually call little s, or sigma if it's the population, is 5, okay? What you do here is you put your mean in the middle, and you add 5 over and over again to go to the right. So this would be 25 for this line right here, and then 30. It tells you how to spread out your data. Our data from this side to the point where we almost can't see anything anymore because the line's really close to the x-axis. That's kind of like where your outliers would be, or really weird numbers we're not expecting. That stretches from like 20 to 35. You subtract the 5 to go the opposite direction to see how far you stretch to the left, and it should be symmetric. So notice this stretched 15 total because we went 5, 5, 5. This one's going to stretch out 15 total in this direction. So this is going to be subtract 5, we get 15, subtract 5, we get 10, subtract 5, we get 5. Okay. Now, the rule that we're talking about right here, it's called the empirical rule. It's on your formula sheet. It's just a little blurb. It gives you these 3 percentages. It's a rough estimate for what percentage of the shaded area, if you shaded this area from the line right here, if you shaded all this, like, let me highlight it. If I shade from here to here and shaded all that area, imagine it all being shaded in. Those arrows right there, that first grouping right there says that a roughly 68% of all the data in your list should be between then 15 and 25. Okay, because those are those values that mark the mean plus 1 standard deviation and the mean minus 1 standard deviation. If you go another standard deviation on each side, so now we're going down to 10 and all the way up to 30. Not if you shaded this area, we shaded from that line to that line, that would be about 95% of the data in your list. Okay. And then if you go one more standard deviation, so 3 standard deviations on each side of the mean, so from 5 to 35, so almost 100%, 99.7% of our data, if you had the list of data in front of you, would be numbers between 5 and 35. Okay, so that's what this little empirical rule tells us. A lot of times people will just call it the 68, 95, 99.7 rule. Now, if we are, and this is really beautiful when they step equally out in each direction. Notice this went 1 standard deviation in each direction. The second line went 2 standard deviations in each direction. So it's got that symmetry. And then 3. So that's why we're getting these nicer groupings. Okay. Sometimes I might want to know what's the percentage of things from 15 to 30. Well, I didn't have a line up here that goes from 15 to 30. I have information, but I don't have an exact percentage for that match because that's 1 below and then I went 2 above. So that's where this next little graphic comes in to help. This is not something I made up. I created this from the information up here. Because there's symmetry, remember this to this is supposed to equal 68. That's what the rule said, from 1 below to 1 above. And this time they're using mean as the population mean, and the little sigma was the standard deviation. So again, those are interchangeable depending on if it's the population or the sample, okay? So I took the 68 and just cut it in half since there's symmetry. So 68 divided by 2 is how I knew that these were 34% on each side. Once we start getting into the different obstacles beyond that, it gets a little trickier. So from the red to the red, so we're overlapping with the pink, that's supposed to be the 95%. Okay. Well, the problem here is I've already done 68% of that because I did it in the pink. So we do 95 minus 68, but that gives me both red areas. So I only want this 1/2, which they're equal to each other. So if we take our calculator and check this, 95 minus 68 is 27%, and we're splitting that equally on each side of our mean. So that's where we get 13.5, okay? And then we've got 2 more rounds, okay? So then we've got from the blue starting line all the way to the blue ending line over here, which we've already used, red and pink. We've already used most of that. This is supposed to be 99.7, right? Because that's 3 standard deviations in each direction. So this number right here came from doing 99.7 minus the 95 we already took care of because we already did red to pink. I don't know why it keeps making that into like a shape. It's supposed to be a 95. And then we cut it in half because we want to equally split it on each side. So let's check that. 99.7 minus 95 is 4.7. Split equally on each side is 2.35. Now you might be wondering, well, how in the world did I get these little 0.15%? Well, the whole number line is 100% minus 99.7 that we already used. I really do not understand why it keeps giving me these weird shape things. Oops. And then it jumped. There we go. So 99.7. And then we're dividing it by 2. So let's check it. So there's 0.3, I believe, is what you get when you do that subtraction. And then again, symmetry on each side. So we're cutting it in half. So 0.15%. Now, there are other, if you Google like this breakdown on like any other kind of website or other books, sometimes they'll go a little further with decimal points because they had different values to start with. Here, I've seen that. These are the ones we use in our class, okay? So I always say if you know these three numbers, it's really good to know how to create this because then you can answer a few more questions. Now, it's not every question because we're going to find out really quickly. This is still very limited and I can only talk about probabilities or percentages between certain exact values that we get down here on the bottom. If I wanted to know what percentage of people scored a 33 or higher, that's not even on my chart up here. So like I would have to figure out, and that's the last section we're going to do in the video today. How in the world would I handle a number I don't see on the bottom? Okay. But let's first practice with these. Okay. So we're going to practice using the empirical rule based on what we know. So assume that a test is normal. That means we can use the bell curve or the normal curve, whichever way you want to call it. And it has a mean of 100. So we're putting that mean in the middle. Okay. So let's put that in the middle right here. The standard deviation is 20. So when we go this direction, we're going to be adding 20. When we go this direction, we're going to be going to the lesser side of the 100. So we're going to be subtracting 20. Okay, this is how we spread it out. So this one would be 1 standard deviation above is a score of 120. 2 standard deviations above would be a score of 140. And 3 standard deviations above the mean would be 160. Okay, 20, 20, 20. All right, subtracting 20. 1 standard deviation below the mean would be 80. 2 standard deviations below the mean would be 60. And 3 standard deviations below the mean would be 40. So like we said, 99.7% of our data, if we had all of these students' test scores in front of us, if we had all the raw scores, 99.7% of them scored between a 40 and a 160. Remember, those are those last extremes, okay? Now, I'm going to look and see what I can do with this. Okay, so they're asking me a lot of random questions. Some are less than, greater than, so I probably should get all the percentages. So remember we said if you take the 68 and split it in half, that gives you 34 and 34. And then we'd have, so that's 68%. So I like to write both information here. The next group, so I'm going to change colors from here all the way to here. So 2 below to 2 above, that's 95%. And again, I'm not going to show all my work on here because it'll get a little messy, but I'll do it on my calculator. We take 95 minus the 68 that already overlapped it. That's 27. You cut that in half. So both of these columns are 13.5%. And once you do this enough, you really do memorize these sort of, at least a couple of them. The nice thing to note is if you just memorize 3 of the ones on the right side or the left side, this has to add to 50%. So sometimes people will use that trick to find one of the missing ones. I did that when I was in school, but you can always recreate it using the method that I'm showing. And then let's change to maybe a different color. Maybe purple. Okay, so from 3 standard deviations below to 3 standard deviations above, that's supposed to be the 99.7%. So we're going to do 99.7 minus 95, which is 4.7, and then split it on each side. That's where we get this 2.35. That one's always the weird one I had trouble memorizing when I tried to memorize it. So I always just had to recreate it. And then we said it was 100 minus the 99.7. And that's 0.3, and we cut that in half. That's how much is on those little tails, the very, very tiny tails. So that's the 0.15%. Not even a full percentage. Okay. Now we can answer our questions. So less than 100 means anything to the left of 100. So that's actually 50%. And that, I know that without adding those up because that's exactly the mean. And we're doing 1/2 of it. So less than is 50%. Greater than would be the other 50% because that's in the dead middle of our distribution. The percentage of scores greater than 40. Okay, so that's from here all the way over. So you could add all of these up, or you could just subtract the 0.15 from 100. That might be easier. So 100 minus 0.15 is 99.85%. Most of the data is greater than 40. And then between 60 and 120, let's use a different color. So here's 60, here's 120. Okay, so this is a useful time to have these little percentages because notice this one's 2 below my mean, but this one's only 1 above. So I can't use 95% because that goes from 2 below to 2 above. We're short of that. So we need to add those three together. So 13.5 plus 34 plus 34. So that's 81.5%. Okay. We're going to do another one. Says the length of pregnancy terms for a particular species of mammal are nearly normal. So again, bell curve with a mean pregnancy length. They didn't even tell us, but they told us the standard deviation is 18 days. So I don't even know what this number is, but I know to go this way, I have to add 18, and to go this way, I have to subtract 18. Okay, so that's all I know so far. About what percentage of births would be expected to occur within 36 days of the mean? Okay, so if you add 18, so let's imagine for a second this is 0, just because that might help us visualize it. If you add 18, you'd be at 18 days more, and then 36, and then what is that? Is that 54? Okay. If we subtract 18, we'd be at negative 18, negative 36, and negative 54. So imagine this being like your birth, the date that they told you the baby should be born. They asked us what percentage of births would occur within 36 days of the mean. Now, that doesn't mean only 36 days late. That horse could have had the babies up to 36 days late, which would go to this direction. Or they could have had the baby 36 days early or less, right? Anything that's between 36 days early to 36 days late of the actual, average due date would be within 36 days of the mean. So the question is, do I even need to know the mean to know this? No, because this is 2 standard deviations below to 2 standard deviations above. This is the 95%. So if they have, and again, I don't know what the actual average is, so I just put 0 in as a placeholder. But if, a pregnancy for a horse or a mammal, whatever mammal we're talking about, I just threw out a horse because I don't know, for some reason that seemed like that was how long horse's deviation was. I have no idea. But let's say that the mammal has a pregnancy average of 120 days or something like that. We could have the baby 36 days before that 120 day mark or 36 days after. But either way, because the standard deviation is 18, that's 2 standard deviations of either side of the average. So that's the 95%. So you didn't technically have to know the mean since this is 36 is a multiple of 18. It's a double. Okay. All right. Number 12 is on the Kahoot. So we're going to skip that one real quick. So we'll look at number 13. Suppose a random sample of adult women has a sample mean height of 64.3. So I'm going to put that down here. And a standard deviation of 2.4. So we're going to have to do a little more work on this one to get all of our numbers. So we're adding 2.4 to go this way, subtracting 2.4 to go this way. Okay. So I've got 64. I always do the addition first. So plus 2.4 is 66.7. So I'm going to write these down as we go. We're going to take that number and add another 2.4 to it. That'd be 69.1. Okay, and then we're going to add another 2.4, which is 71.5. And then we're going to go back to the 64.3 and subtract the 2.4. Minus it, that'd be 61.9. Oops, why does it keep thinking my 9s are these weird rectangles? It's very, very weird. Minus another 2.4 is 59.5. And minus another 2.4, 57.1. Okay, so I've got all my inches down here on this part. So between what two heights are approximately 99.7% of the data? So remember 99.7 goes, and I'm going to highlight this, 3 below to 3 above. So that's going to be 50. So we would say about 99.7% of women, adult women, are between 57.1 inches tall to 71.5 inches tall. So that's almost all women, okay?
Use the empirical rule to determine the approximate percent of height that lies between 59.5. So I'm going to mark this in a different color. We'll do blue. Okay, so that's this number all the way up to 69.1. Okay. Well, this is 2 below to 2 above. So anytime it's an equal split, we went exactly the same amount on each side, 2 big columns essentially. That's one of the special rules. So this one is the 95%. So 95%. So that's just using that empirical rule. Okay. And then there's 2 more on this section. I'm probably going to just post this as a PDF because this video is getting very, very long. So I will post the PDF with this. So please check 14 and 15. They're the same thing we were just kind of doing. But I just want to make sure the video is not so long for y'all to watch. So check these. I'll put a little note for myself to remind myself to post this as a PDF. Okay. So that you can see those. All right, so that takes us to our last section in the notes. Now, 7B2 is also a homework. It's an Ivy Learn homework, not a Newton homework. You'll see that it's a little different. But I completely covered that topic in the pre-video for this week. So those www videos. So make sure you've watched your www video anyways, because you need your points. But that actual 7B2 homework is completely covered since there's only one type of question really to it in the pre-video for this week, okay? So we're just doing this last part. Find and interpret what are called z-scores and reading the probability from a z table. Now, we already know about the normal distribution and what the standard deviation is and how that spreads out our bell curve from our center. We already know all of these little facts. These were all in the last section. What we want to know is what if, and let me go back for just a second to that last problem we actually did together. If I'm not any of these heights, like this is not my height at all, none of these. So if I wanted to actually place myself on the bell curve, I am about 5'6". So that would be 5 times 12 is 60, 66. So I'm just a tiny bit, I'm not quite here. I'm just a tiny bit shorter than this first mark right here. But that would change the percentage because I'm not on that exact mark. So if I wanted to know how many people were shorter than me, I would need to find a way to convert myself to this position. Where am I? And then how would I know what probability is attached to that? And that is the whole idea of this last section. Okay. So the 68, 95, and 99.7 rule applies to data values that are exactly 1, 2, or 3 standard deviations above or below the mean. They do not help you with any other values that are on the number line. So that is why we need a better method. So we're going to do something called converting our raw data into something called a z-score. A z-score, what it essentially is you can take any set of data that is normal. So if it's got a bell curve, we can take it. And instead of putting the number for our mean as the actual number, we standardize that value to 0. And then the standard deviations that we're used to seeing just become 1 above, 2 above, and 3. So it's just 1, 2, 3. The ones where we go below the mean are -1, -2, and -3. And these are going to be what we call the standard normal values. Now, I was just a little bit less than that first standard deviation with my height. So if I convert my own height to a z-score, it'll give me a decimal point very close to 1, but not quite. Okay, so again, I'll show you as an example of that in a minute. But why we want to do this is because that doesn't matter if I'm dealing with test scores, weight, inches, whatever, height, whatever we're dealing with. If it's normal, if the data is a bell-shaped curve, we can turn it into the scale between -3 to 3. And there is a table that we're going to see that tells us those probabilities. So that's why we want to standardize it. So if you get a negative z-score, we know that's to the left of our mean. Our mean is the 0 in this case. If we get a positive z-score, we're to the right. Okay. And I don't know why there's an extra digit in there. That should have just been 2.2. And if you get 0, you're at the mean. Okay, so that's just what this kind of summarizes. Now, this is the formula that we use to convert any set of data that we have to the z. So to figure it out between -3 to 3. So essentially what you do is you take the person in question. So say we're talking about people's heights or weights. The specific person you are looking at is your data value. The mean is for all of the data. So they would have told you the average is this. And the standard deviation is also for all the data. It's how the data spreads out. So you do your item in question minus the mean divided by the standard deviation. That's all it is. Okay. So let's look at this example. The birth weight of infants born full term in the US have a normal distribution. So they're telling us it's normal so that we can do this formula. Okay. The mean is 7.7 pounds. The standard deviation is 0.85 pounds. So that's for all US babies that are born full term. That's their average and their standard deviation. What is the Z-score for a specific infant that weighed 8.5? So we're putting this one infant on our scale, okay, to see where they would fall on the bell curve. So take the item in question, which is that specific baby, minus the mean, and then we're going to divide that by the standard deviation. This will convert this to a number between -3 to 3, so we can see where it falls on the scale. Like, where would that baby be? So, and usually we round these to 2 decimal places, so it's going to be 0.94. So if you think about where is that baby on the bell curve, here's 0. And then remember we had our 1, 2, 3. Those are the standard deviations above. And then -1, -2, -3. Those are the standard deviations below. Again, the 68, 95, 99.7 works for those. But this baby is about right here. So I'm just going to put a little X right there. So that's where that 0.94 is. It's just shy of that mark for that first standard deviation. So if we wanted to know how many babies weigh less than that specific baby, we can't just use this one. We'd have to look up the Z-score for 0.94 in our probability table. And we are going to show you how to use that in just a minute, but that's kind of what this is leading towards. But the answer to this actual question was just, what is the Z-score? And what does that mean? This baby is 0.94 standard deviations, because it's not quite a full standard deviation, above the mean because it's got a positive Z-score. Okay. All right, let's look at another one. So driving speeds on a 2-lane highway are normally distributed with a mean of 55 miles per hour and a standard deviation of 4. A driver is pulled over for driving too slow on the highway. The state trooper recorded the driver's speed at 40. What is the Z-score? So again, we have a specific driver's speed. So that's our Z-scores raw item. That's the item in question. So 40 is that person's speed. The average of all cars is supposed to be 55. And the standard deviation of all cars on that highway are supposed to be 4 miles per hour. So 40 minus 55 divided by 4, it's -3.75. So yes, I absolutely agree that this cop should have pulled this person over, because if you think about what that means, here's 0, here's 1, here's 2, here's 3, and these are all the negatives, right? Because they're in the left side, and then there's 1, and there's 2, and there's 3. A -3.75 is way down here, right? This person is in that 0.15%. They are driving they're actually way lower than that, actually. They're pretty far away from that. They're almost at -4. They are not a typical driver. A typical driver would be between the -3 to 3. This is an outlier. This is someone doing something odd, okay? So that maybe they're drunk, maybe they're doing something not supposed to be doing. The state trooper was well within their rights to pull that person over with that much of a deviation from the norm, okay? Number 3 is on a Kahoot, so I'll let y'all try that one. The birth weight of newborns at a local hospital have a normal distribution with a mean birth weight of 6.3 pounds, standard deviation of 0.5 pounds. A newborn is chosen at random with a birth rate of 5 pounds. So that's the baby in question. How many standard deviations? Again, how many standard deviations above or below the mean is your position. That's your Z-score, is a birth weight of 5 pounds. So calculate the Z. So Z equals 5 minus the 6.3, because that's the average, divided by the 0.5, which is the standard deviation. So always the baby in question minus the average for all the babies divided by the standard deviation for all the babies. So this is a -2.6. When you write the actual Z-score, you will put that negative number. You will put -2.6. For the interpretation sentence, you do not put the negative on this part. You just tell us how many values are we away from the mean, and you tell me it's negative by choosing the word below, okay? So you do put the negative when you're writing the Z value, but when you write it as a sentence, you just say, I'm this many and then you tell me below or above, depending on if it's positive or negative. So negative would be below, okay? All right, let's look at number 5. The test scores in a chemistry class are normally distributed with a mean score of 75% and a standard deviation of 9%. A specific student scored 93. Is this unusual? Okay, so for these on your homework, you have to really read these carefully because they tell you what they consider unusual by telling you if it's more than a certain number of standard deviations away from the mean. If you don't look carefully, sometimes this is 3, sometimes this is 2. So always read this carefully. So first thing we're going to do is find that z-score. That student scored 93. The average for the class was 75, and the standard deviation was 9. So we take that, 93 minus 75, divided by 9, and that's a 2. Okay, and it's positive. So my z-score is a 2. A test score of 93% then is, and since they said as long as you're, they said we would be unusual if we are more than 3 standard deviations away from the mean, okay? So this is not unusual for this class because the standard deviation is not more than 3 standard deviations, and for this case, it's a positive, so above the mean. So these, you really have to read it back to yourself a couple times to make sure you've chosen the right sentence structure, okay? It's not unusual because they said unusual would be further than 3 away. All right, let's look at another one. Now, I believe on this one, I needed to change something. I actually had this work out exactly to 2 for the z-score again, and that would mess up our whether or not it's unusual because they're asking for 2 standard deviations. So just on your paper, change that to, oh my goodness. I really don't know where these rectangles are coming from. It keeps wanting to put them on there. We're doing 395. So just change that to a 395. Okay. So that's the number of customers they had on a specific date. And the average is 300 and the standard deviation is 45. So we're going to do our z-score first. So 395 was a specific date. Average usually is 300. Standard deviation is 45. Okay. So 395 minus 300 divided by 45, that's going to be a 2.11. We usually round our z-score to 2 places, unless they tell you differently, okay? So my z-score for Saturday's crowd was a 2.11. Now I need to look at what they're talking about. They said as long as we're within 2 standard deviations, we are going to be okay. So this is 2.11 standard deviations above the mean because it's a positive z-score. This, I would say, is not unusual, or actually, no, it is unusual. Sorry, because they said we need to be within 2. We're actually further out than 2. Trying to talk and write. So this is unusual because the number of customers who ate at Grady's Grill is not within the 2 standard deviations of the mean. So sometimes the way they word this, when they say more than or within, you have to really be careful. More than means further away from the center. Within means you're inside that center. You're between -2 to 2. So just be really careful. These are not usually ones we put on the test part with the little drop-down menu because they change the wording too much. So just go slow with those on your homework, okay? Now, once you find that z-score, like that 2.11, what does it mean? Well, if we can figure out how to read the probability, which is why someone came up with a chart for this, we can then tell people what percentage is less than you or what percentage is greater than you, your specific data value. So the charts that we give you, they only give the area or the probability to the left. So every time you look at these little tables, I'll show you what they look like. If my z-score is 1.12, I go to 1.1 and then go over to the 0.02. This 0.8686 is only the area or probability less than me. It is less than only, okay? So the tables always read less than or left. If you need probability greater than, taller, higher, more, heavier, bigger than, okay? The whole curve adds up to 1, because remember it's 100%. So you can do 1 minus the chart value you get to get the greater than. So whatever you get from the chart, it's going to give you this, okay? 1 minus the chart will give you the other half, okay? Or the other side of that value. So that's what it means, okay? So let's look at this. So it says below is a portion of the standard normal table. So on your homework questions, quizzes, and on for the exam, if we give you a problem where we want you to read the table, we include a little zoomed in version of the table for you. So we want to find the probability to the left of a z-score of 1.26. So 1.2 is here. The 6 is in the hundredths place. We find where those overlap. That is this value right here. That is exactly what we want because when you're going to the left, so imagine where that z-score is. 1.26 is above the center because it's a positive. This area is 0.8962, or the probability. It's area and probability at the same time. 0.8962. Now, if you want to go to the right, it's different. You have to go find the z-score, so 1.32. That's going to be here. That's going to be this value. When you're going to the right, we do 1 minus that value because we want the area above, not below. This chart only gives area below. So if you're at 1.32, which again is over here pretty far to the right, this is going to be that 0.9066. The table gives you that. We want this. We want the upper part. So when we want to go to the right, we do 1 minus it, and that's 0.0934. So that's the answer for that. Okay, so left, you read directly from the table. Right, you want to go 1 minus that. Okay. All right, this is on the Kahoot, these two. So let's look at the last couple ones here. We're almost done with this video. If Erica's exam, that's supposed to say score, has a z-score of 1.35 and the data is normal, what is the probability that a randomly selected student scores higher than Erica? So higher means to the right. This is to the right. So whatever we look up for Erica, we got to do 1 minus that. So 1.3 and 0.05, this is the to the left value. So we want the higher than that. So roughly 91% of the students scored lower than her. We want to know how many scored higher than her. So 0.91. So about 0.0885. Okay. Determine the area under standard. So we're going left of just 1.44. So nothing to do here except for read from the table. Left is always the easiest one. So 1.44, that's going to be 0.9251. Okay. All right. And then 13, we have find the area to the right of negative 1.90. So if it's a 0 at the end, you just use this first column right here. Now, that's to the left. So you got to remember, negative 1.9 is way down here at like almost -2. This little tiny percent or area, probability, however you want to think of that, that guy right there is to the left. We want this part right here. So we have to do 1 minus that. Okay, so left is always the table, right is 1 minus the table. And so this would be, there's 9713, so almost 97% to the right of that value. Okay, so always be paying attention. Are we going greater than? Are we going less than? Okay, and then the last thing, this is it for all the notes. Percentile. Percentile is directly related to what I was just saying. That's why I sometimes call these percents because they're in decimal form right now. This is about 2.87% if I change it to a percentage. A percentile tells you what percentage of people scored below you. So it is exactly directly related with all these little decimal values in this table are percentages in disguise where they tell you the percent to the left. So they're technically the percentiles. So it says in statistics, a percentile is a term that describes how a score compares to others from the same set. While there is no universal definition of percentile, it's commonly expressed as a percentage of values in a set of data scores that falls below a given value. So values to the left. So if the mean on a normally distributed exam is 71 and the standard deviation is 9.2 and Joe earns a 52. So let's find Joe's z-score. So 52 minus 71 over 9.2. We're going to find where Joe ranks. 52 minus 71 divided by 9.2. Now notice, this is not the actual percentile. This is the z-score. This is her position on the z table. Okay. What percent of those taking the exam will score lower than Joe? So we need to go and look at negative 2.07, which I did have on this table right above here. Negative 2.07. And that value where those overlap is 0.0192. to 0.0192. That's the actual decimal version. We turn that into a percentage and round it to the nearest whole percent. Roughly 2% of students scored lower than Joe, to the left of her. So Joe is in the second percentile. That's what we call it. So if it was a 98%, we would have called it the 98th percentile. Joe scored higher than only 2% of those taking the test. Okay. That means the opposite of that is that 98% of people in this class scored higher than Joe. But the percentile is always written in a way where we are telling how many people scored less than you. Okay. All right, and that's it. So I'm going to go ahead and stop this video. I'll have some announcements to this week. This one's going to be an announcement with the PDF file for the 2 problems I skipped. And then it'll also have the QR code for the Kahoot, because remember, I skipped problems that I said were on the Kahoot. Make sure you complete that after you watch the video. Other than that, just make sure you don't show up to class on Thursday, since we are not meeting. This is in lieu of our class, since I have to be in commencement stuff. And just send me messages if you have any questions in general. Okay, wonderful day.